Okay, here we'll talk about the idea that we have on the FM, that is the upper symbol. Now, this was invented for a certain purpose. The necessity of this came with the same idea of compounding interest, but it came in a different direction. And I'll explain what I mean. The idea, the concept of dividing things into tiny pieces, this is what drove mathematicians in a very high, up on a very high mountain, and caused a lot of new math to sprout out. Calculus, other stuff. This idea of limit, and let's get the most simple, concrete example of what this is all about. We know that we can make a triangle, we can make a square, a pentagon, a hexagon. So here comes the very simple, primitive question that every person should ask when he fiddles around with these shapes. We can find the area of a square, of a triangle. We see the area grows a little bit. Now, the condition is that from the center of these figures till the vertex is a certain, let's say, 1 inch. So we can figure out what's the area of a triangle in such case, what's the area of a square. The way to do it is to make it into small wedges, triangle wedges, and then to figure out 4 times these wedges. This is the very simple, everybody that just works around a little bit with pictures enters his mind. Then here comes the interesting question: how about if I make a 10-sided figure, a 20-sided? So the guy starts realizing here, interesting thing that happens. It gets a little bit bigger, but here's the big but. It tends to a limit. It doesn't get endlessly bigger. It gets bigger and bigger, but every time it gets only with a tiny drop bigger, and each time you add another side to this figure. Let's say you have a 100 sides, it's going to be a tiny amount more area than that if you have a 50-sided figure. So here comes the question: what is if you have an infinite amount of sides, and we call that a circle? What will be the area? So we know the circle of an area. The area of a circle is pi r squared, but just not the concept of it is based on a very intuitive reasoning that there are things in nature that get a drop bigger, but they get so tiny drop bigger that even if you make them endlessly, they'll still not be over a certain border. This is the concept. The same concept is asked: a half plus a quarter plus an eighth plus a 16th. You can go endlessly down the line. It will not be bigger than 1. A half plus a quarter, it will always get closer and closer to 1, but never pass the limit of 1. This is the basic stuff that we call limit. Now, where does this apply to financial mathematics? So here's the same idea. It started off with this idea that a guy puts in $1 and he gets interest. So let's make a very simple case. He puts in $1 in the bank account, and then the next year is 10%, so he ends up a year from now with $1.10. Now, if the guy puts in the $1 in the end of the year, then how much does he have at the end of the year? He has $1. So here are the two extremes. He puts in $1 in the beginning of the year, he has $1.10. He puts in $1 at the end of the year, he has $1. How about a lot of interesting things can happen? He puts in the bank account 50 cents today and 50 cents in a half year from now. So on 50 cents he gets 1.50 1% interest. On the other 50 cents, he gets only the root of 1.1 interest. You have to add together these two, that you'll know what's going to be his final number. How about if he puts in a quarter now, 1 quarter, another quarter in 3 months from now, another quarter, another 3 months from now, then another 3 months. So it's for January 1, he puts in January 1, April 1, July 1, October 1, September 1. So how much will he have at the next January 1? So here, just very simple. Since we said there's 1.1% for the whole year, so it's the fourth root of 1.1 that you accumulate for a quarter of a year. So you take that, so the first quarter you get fully 1.1% interest. On the second quarter you get 1.1 to 3/4 of root. Then you get to a half a root, and you get to a quarter of root. You add them all together. So we have pocket calculators today. It's very easy to do. You just have to enter in the fourth root. You have these exponents. You put into the power of a quarter, power of 3/4. Now, if you get curious, so naturally, you try to fill it around. How about the 5th, the 6th, the 7th, the 8th? You can do, and why can't you divide a year into 1,000 pieces? Theoretically, 1,000 pieces will be like every few hours of a day, because a year is 365 days, so 1,000th of a year will be about 3 hours. And how about the millionth of a year? How about? But here's the interesting part, that it tends to 11th. Meaning to say that you'll not be a millionaire. Even if you put in every second, or every split second, again, you put in not a full dollar, put in a millionth of a dollar, every millionth of a year. So, what is the final accumulation of all this putting in the money? The answer is such an interesting thing that is called logarithm. The answer will be, you'll have the logarithm of 1.1. That's how much you will have by the end of the year. And this is a number that is less than 1.1, because that will be if you put in the full dollar now, full dollar beginning of the year. It is more than 1, that will be if you put in the whole dollar at the end of the year. It's in between 1 and 1.1. Get this point. It's not as good as putting in the whole dollar at the beginning of the year. It's not as bad as putting everything at the end of the year. It is somewhere in between, and that's why it will be the logarithm of 1.1 is a number that's in between 1 and but you have to add 1. This only tells us the addition. So it's actually logarithm of 1.1 plus 1, if you want to know the full number. Again, logarithm of 1.1, that is that's a fraction that's in between 0 and 0.1, and you add 1 to that. That will be the final amount that you have accumulated end of the year. And how this is done needs another video, but this is just explaining what exactly happened here with this story.